Okay, we're back. So this is the location of all the hotspots in the world. Notice that most of them are in the oceans, the oceanic hotspots. And you can even see the track of where they occur. And the reason is that we can see those track is due to this kind of phenomenon right here. And what this kind of went off that last topic where the youngest volcano is going to be where the hotspot is, the oldest is going to be further away. The reason is this: the hotspot stays put because it's underneath the asthenosphere. But the lithosphetic plate that goes over it is moving. And so if you have a hotspot here and it burns through to form a volcano, it's going to move in this direction, causing another volcano to form with the old volcano out here. Keep moving, another volcano down the line, and these volcanoes go further and further away. So you end up with this chain of volcanoes. Like Hawaii is a great example of these. Okay, you can see Hawaii, and then it keeps going all the way back, all the way to the Emperor Trench, right off the coast of Japan. Okay, and you can see this in other places too, where you see the Easter Island, Samoa. All these little places are these old chains of volcanoes. Now what's cool is you go back and date the ages of all these little islands all the way across, and they get older and older and older as you go apart. So notice that the plate's moving in this direction, so the actual plate is moving parallel to the direction in which the islands are oriented. Okay, but notice that at one point they all moved a little bit. So the movement of the plate kind of shifted a little bit back right around this area. And this is actually where Midway is. If you know anything about World War II history, Midway was where we actually stopped, had a big battle there. And this is where we actually stopped to actually start flying out to Japan to drop the bomb on Hiroshima in those areas there to end the World War II. Anyways, the point comes is that island of Midway is actually an island of the Hawaiian volcanic chain. Okay, it's no longer active. It's been slowly, because as it goes away, it's nice and hot, and so they sink slowly over time, and some of them even go underneath the water to form what we call seamounts. But if they're right above the surface, like Midway is, it's actually a nice place to actually land your airplanes and so forth. Okay. So that's just an example of an oceanic plate boundary. These ones have lots of volcanoes associated with them, mostly mafic volcanoes, so therefore shield volcanoes. Because remember, it's a mafic material from down below, coming up, and therefore you end up with mafic volcanoes. Make sense? We always have lots of cinder cones with these because cinder cones could be in none of these, but usually on the lower end of mafics. Okay. Now, if this actually happened in a continent, it would have to burn through that continental crust, and so therefore it's going to be more felsic. And so when these eruptions occur, these are going to be big eruptions, huge eruptions, such big eruptions that they're going to cause disaster all over the world. Okay, Yellowstone eruptions have occurred, don't occur as often as Hawaiian eruptions do. Hawaii has been erupting since 1983, almost continuously. Yellowstone eruptions have occurred about every 2 million years or so. A large crater is formed, but smaller eruptions occur about every 630,000 years. We're about 30,000 years overdue. But remember, the error bar, as we talked about last time, is about 100,000 here or there. So we're getting close to when another volcanic Yellowstone eruption should be occurring soon. Okay. Notice that it's once again parallel to the direction in which the plate's moving. The plate's moving in this direction, so therefore it appears as if the hotspot moves the other direction as it goes. Okay. So this is an example of a continental hotspot. And these ones you tend to have a combination of both mafic volcanics and felsic volcanics, but not much intermediate in between. And most of that comes because you first burn through the material, forming a big eruption for the felsic stuff. And then, now that you have a conduit to go through, basically, all that mafic stuff comes out from this asthenosphere below. Okay, so you have a combination of that. So if you look from last week, when we had a lot of those basalts that I got from Idaho, they were getting from the basalts of the Yellowstone hot spot after it went past that initial explosion. So we had lots of basalt because of that. Now, there was one sample that had lots of rhyolite and things like that in it that was much more felsic. That was the Lahar Deposit, if you remember, and that came from Yellowstone during one of the big eruptions. Okay, so there's different types of volcanics associated with it there, but these are very, very dangerous and very, very big eruptions. One of the biggest eruptions in the world. We often call them supervolcanoes. So, How does plate tectonics affect the distribution of life? Well, this is important. This actually impacts evolution and biology and things like that, right? And they have. So if you think about it, because remember when Africa and South America and North America were all together, well, animals can go back and forth freely, and the evolution of those animals actually occurred all the time. But then you separate them. Some of those organisms are on the east side, some are on the west side, and now they can no longer actually interact with one another. So they'll start becoming what we call geographical barriers. Those geographical barriers will cause one organism to actually go off in this direction, one organism to go off in the next direction. We see that in the fossil record, of how the organisms actually changed over time, where some organisms actually, which were similar to each other from Africa and from South America, diverged about 250 million years ago when they separated apart, and therefore now we have these two different organisms on both sides. Okay. Also, this can actually influence climate. So like the Himalayas has a huge impact on climate in the area, causing all the air to rise, therefore causing a desert on the other side. The Himalayan plateau is a huge desert because all the snow and rain actually die out on one side of the mountain range. And we'll talk more about that when we talk about weather. But the point comes is there's big biotic provinces of areas where only certain plants can live and only certain animals can live. And these different barriers actually form because of the mountains or because of an ocean basin forming and things like that. So here's an example. Back during when the Pacific Ocean and the North America and South America were not connected, the organisms could go back and forth freely therefore all the organisms were fairly similar to one another, right? But over time, they formed these volcanic arcs through here and slowly filled in this. And now we have this Isthmus of Panama, these areas here where there's this big line or arc of volcanoes that attach North America to South America. Now these organisms can't migrate back and forth with one another, and so now they're different. They've evolved slowly over time to actually cause the Pacific organisms to be different than the Atlantic organisms. Okay. Well, how does this also, plate tectonics, distribute the distribution of our resources? Does it as well? Because remember, where we have volcanics, we're going to have certain types of resources. Where we have sedimentary rocks, we're going to have certain types of resources. And this is going to cause the uplift, causing things to erode, to form the sedimentary basins, to get where we can get oil, gas, shale, things like that. Places where we have volcanics, we're going to get more gold and silver and things like that. So the plate tectonics is a great way we can figure out where we're going to find gold, where we're going to find silver, where we're going to find oil. All of these resources that we use every single day is all based off of understanding plate tectonics. The distribution of life is based off of the distribution of the plate tectonics. The distribution of our resources is as well. Tectonics is a big, big idea that impacts not only the geosciences, but the biological world as well, and the atmospheric sciences. So remember, our world is a system where the geosphere, the biosphere, the atmosphere are all working together. The hydrosphere are all working together, are all kind of work in one big system, and they influence each other over time. Okay, guys, that's plate tectonics for this time around. It is an important concept. You might need to go through it a little bit and kind of make sure you're understanding it. We will tie in ideas from earthquakes that are going to be coming up into this as well. I tried to tie in volcanics, which we talked about before, into this, and igneous rocks, which I tied into this before. Didn't tie in the sedimentary rocks as much, but we will a little bit later. The whole idea here is this idea ties in a lot of the concepts that we've already been talking about. It's a big idea. It's one of the most important ideas that you're going to be learning about this semester. Okay. Talk to you guys next time. Hope you had fun, and hope you learned something. Talk to you later.